Okay, this is Unit 3, Section 5.2, where we talk about friction. All right, you guys may have talked about friction already. You may know it a little bit from before. But to get started, I'm going to show you guys the spring scale. So hopefully you guys can all see the spring scale. You guys see the spring scale?
Are you talking to them or us?
Yep, I'm talking to all of you. Oh, crap.
Hi, YouTube.
Wait, we're
Nice
recording
job, Brad.
this hour?
Yeah, we're recording this hour.
Follow me on Twitter.
Now you didn't warm your voice up for all your questions?
I gotta
All right.
start over.
So-
I'm not ready for this.
Not ready for this. Me neither, obviously.
So are we
All right.
going
So, here's the spring scale. Okay,
Oh, you need some lotion.
I do. So, can you guys see that? All right, I'm gonna pull my box, which you guys can hopefully see, with the spring scale. Now, I'm pulling on the hook end, which changes the force applied, and hopefully you can read that force. Now, right now, there is a 3 Newton force acting on the spring scale. You guys see that?
Yeah.
Okay. So, there's a 3 Newton force acting on the spring scale, right?
Yes.
The box is attached to the end this way. The box is experiencing a force of 3 newtons, pulling it to the
Left. On the left, you're right.
okay, pulling it to the right, to the left, whichever. The box is experiencing a force pulling it one direction, right? There is a force acting in the other direction because the box is stationary. The box has no acceleration, so we know there has to be a force going the other way, right?
Yes.
What's that force going the other way?
Friction.
Friction.
Friction. Okay, so I'm gonna pull on this rope again. Right now the scale reads 2 newtons, right? So I'm pulling it this way, right?
Yep.
The force of friction pulls the box that's attached to the string, which is attached to the spring scale,
The other direction.
in the other direction, right? Okay, right now the frictional force equals how much?
3.
3. What about now?
1.
1. What about now?
4.
4. What about now?
5.
Oh, you see what happened there?
Yeah.
I got up to 5, and then what happened?
Moved.
It moved, and the dial went what?
Down.
Went back down to what?
Like,
Oh, look at that.
3.
wow.
Okay.
It's like a unicorn.
So remember that as I pulled on the spring scale, it got to like 5.5, right? Then once the box started moving, what happened? The spring scale slid back down to
0.
not 0, 3, 4, somewhere in there. It got less, didn't it?
Yes.
Okay. So let's draw some pictures. Now don't forget our observations. Our observations were.
So can we just watch you record?
You can if you want to, but I'm going to turn it off here in a second. The projector messes
We
up.
know
So-
together all of
Our
these.
class.
That's so exciting.
All right.
I can
So-
see your shadow in the shadow.
That's crazy.
I see like 3 branches.
Lucky you.
Every
All right,
second you were caught
so-
up.
What?
Wait, that was
I
really
don't
like,
like class.
what are you managing for using
That was
your
like
data?
160.
Okay. So we learned yesterday that friction is a force that opposes motion, right?
Yeah.
Well, that friction is a force that opposes motion. Right? I want to make sure that I am. Okay, good. I want to make sure that I'm in the screen. All right. So friction opposes motion, right? Now we had a block or a box that was attached to a spring scale, right? And I was pulling on the hook end, so I was applying a force in this direction, right? Now, when that force equaled 2 newtons, did the box move?
No.
No, the box didn't move, did it?
No.
Okay? The box was stationary, wasn't it? So the box felt a pull from me this way. Oh, almost wrote after Mr. Branch. Okay? Felt the pull from me this way, and a friction force going
The other way.
the other way.
Can you fix that?
Monty, come on, son.
All
All right. So there was a pull to the right and a force friction to the left, right? This pull was at 2 newtons at one point, right?
Yeah.
Then what was the force friction equal to?
2.
2. How do you know that, Nan?
Because
Because you just do. Because the box didn't
Move.
move. So the acceleration is
0.
0. Now that acceleration stayed 0 as I increased the pull. Didn't I pull with 3?
Yeah.
So if my pull was 3 newtons, what is the force of friction? 3. Right?
And so on.
If my pull was 4 newtons, what was the force of friction?
They're directly related.
4. Right? When I pulled with 5.5 newtons, what happened?
It moved.
It moved, and then the dial kind of sprung back, didn't it?
Yeah.
Okay. So there was a limit to how hard I could pull and have the box stay stationary, wasn't there?
Yeah.
What was that limit?
5.
5.5. So we said acceleration is greater than 0. Oh, that's an A. Acceleration is greater than 0 when F pull equaled 5.5 newtons, right? that means the block did what? It moved when acceleration was 5.4, or when the force was 5.5 newtons. Does that make sense?
Yeah.
Okay. When the block was stationary, what force was acting on it?
The one ball. That you're gonna write up there.
I am going to write it there, but I'm going to start with a different word. Okay. When the box was stationary, a couple types of friction. Stationary means what?
Static.
Static, right? Static means stationary. So when the box was stationary, static friction was acting on it. Okay? Static friction is friction. Wow, I cannot spell today.
We know.
Friction acting, yes, today,
That's every.
on a stationary object. Now, is this friction constant? No, I showed you static friction wasn't constant, right? When I pulled with 2 newtons, the static friction was 2 newtons, right? When I increased my pull to 3 newtons, the static friction was 3 newtons. So this static friction is a result of the force being applied to keep the box stationary. So this force is not constant. Yes, right, Rex.
What if there's something like hanging by a string and it's not moving at all? Is there static friction on it?
So like if I had just a mass suspended from a string,
Yeah, I'm not.
there is not static friction. Okay, static friction has to be between like the tabletop and the box.
Oh,
All right. Now, static friction comes as an inequality. All right. The force of static friction. Okay. Now you're probably saying, "Whoa, that's an interesting subscript. Is that an M or is it a U?"
it's the it's Greek actually.
It's the Greek letter U, or Greek. No, maybe it's M, but it's called mu. Okay. Mu is the coefficient of friction. Okay? If I have mu s, that is static friction. So this is mu s, this is static friction. Okay? The force of static friction is always less than or equal to the coefficient of static friction times the normal force. You're probably saying, "Whoa, why is the normal force in there?" Yes, Kyle.
Just keep going.
Okay. You're probably saying, "Why is the normal force in there?" Well, think back to when you wanted to wrestle in the living room. I don't know if you guys all want to wrestle in the living room, but I used to want to wrestle in the living room. I mean, we always had to wrestle in the living room. And we always had to move the couch. Right? If we wanted to wrestle in the living room, we had to move the couch. We didn't break the couch. Growing up with 3 brothers, my mom just kind of said, instead of saying no wrestling inside, she said just don't break anything. Okay? So we had to move the couch so we didn't break the couch. Right? So if someone was not on the couch, so the couch was empty, I could move the couch no problem. Right? But if my brother was being kind of a jerk about it and didn't want to wrestle in the living room, and he was laying on the couch, okay, did I have to push harder or less hard to get him to move? Harder, right? Because if he's laying on the couch, that means that the floor is pushing up harder on the couch because now instead of supporting just the couch, the floor is supporting him and the couch, right? So the whole situation revolves around this whole idea of friction. To get the couch moving, I had to overcome static friction. When my brother's laying on the couch, static friction was greater. Okay? This force normal, the surface was pushing up, more difficult. Harder. What? No, and over the course of the last couple of years, I've injured all my brothers, so we no longer wrestle.
How many brothers do you have? 3?
3.
And no sisters.
No sisters.
How did you injure us?
What?
What'd you do?
Well, I didn't really injure them, but they got injured. Like one had a rotator cuff injury. I ran a chicken wing too hard on them. That one tore his hamstring. That was the last
Oh,
one.
you're so strong.
All right, it's just the way I am. All right, static friction. Does this inequality make sense?
Yes.
Does that make sense?
Just a little.
Does the normal force part make sense?
Explain it again.
Okay.
Break it down.
You can also think about it this way. If I'm going to rub my hands together to warm them up, okay? If I just kind of hold my hands together and just kind of move them back and forth, I don't really get my hands warm, right?
No.
I have to really push them together, don't I?
Yeah.
Now, when I push my hands together, they're applying normal forces to each other. As those normal forces increase and I move my hands back and forth, they get warmer. Because that thermal energy your hands are gaining is a result of the friction. So if you push less, you get less thermal energy. You push more, you get more thermal energy. Okay? Now, if you have lotion on, that kind of acts as a lubricant, which decreases the amount of friction. So it's fine. If you have lotion on, you get less thermal energy.
Break down the equation again.
Yes, I am.
Break it down.
What do you mean?
Pieces.
So this is the normal force.
Okay.
That's the upward force from the surface. Okay? This is the coefficient of static friction. It's some number. It'll be a number less than 1. Alright? Does that make sense? Okay. Now once the block started moving, it experienced what? It started to slide. What's that friction called?
Sliding.
Kinetic friction. Kinetic friction is sliding friction. It's friction acting on a sliding object. Okay. Now, once the box started to slide, the little dial on the spring scale went up to 5, right? It went up to like 5.5, and then it got to 5.5, and it kind of bumped back, didn't it?
Yeah.
Okay. Why did it do that? No, I was still pulling with the same force.
No, because it moved.
Because the box started to move, right? So I was pulling the same force, and I said, as the box started to move, it put slack in the string, right? Because the box accelerated, right? Now, when the box accelerated, we experienced sliding friction. And I could have kept the box moving, but I would have ran on the camera angle. If I were to keep the box moving, you think I'd have to use 5.5 or 4? I'd have to use 4, okay? Because sliding friction is less than static friction. Just like when you're pushing that couch, right? If I'm trying to push a couch, it takes a lot more force to get it moving than it does to keep it moving, right? You guys all experienced that before?
Yeah.
When you're pushing a car, if your car runs out of gas, it takes a lot more force to get it moving than it does to keep it moving, all right? Kinetic friction, the equation is F equals mu K, because K stands for kinetic, and this equals mu K Fn. Now the reason why this is an equality and not an inequality, the reason why we have an equal sign here is because this is a constant force. Static friction all depends on the force you apply when you're trying to move it, right? And there's a limit to that force. If I pull with 3 newtons, static friction is 3 newtons. I pull 4 newtons, static friction is 4 newtons. I pull 5.5, I've overcome static friction. Now we start sliding, and I have to apply a constant force to keep us going. Okay? Does that make sense?
Yeah.
Okay. We'll do some more examples of this on Monday, but you have the general idea for your homework. Now these mu's, guys, they depend on the surface. Rougher surfaces have higher mu's. Smoother surfaces have lower mu's.
So like a sandpaper would have a big mu, but a wax paper would have small mu.
Yep, sandpaper would have a big mu. Wax paper would have a small mu. Dang it, I was outside. Oh, I wasn't. Awesome.
That's my fault.
Hi, people
Give
of
me my
YouTube.
phone, Kyle.